400 years ago, we thought Earth was the center of everything. We were wrong. 100 years ago, we believed our galaxy was the entire universe. Wrong again. 50 years ago, we were confident we understood what reality was made of. We were catastrophically wrong. Today, we are facing the most disturbing realization in scientific history. The more precise our instruments become, the more we discover how blind we actually are. 85% of reality is completely invisible to us. The universe we observe is a tiny, fragile shell floating on an ocean of the unknown. If discovery is your thing, subscribe to Stellify Science and turn on notifications so you never miss what the universe reveals next. We are about to explore the universe we cannot see, starting with the moment science realized its greatest flaw. The year was 1970, and in the Arizona desert, astronomer Vera Rubin was adjusting her telescope in the freezing darkness. She was not trying to revolutionize physics. She just wanted to answer one simple question. How fast do stars spin inside a galaxy? Sometimes the simplest questions hide the most terrifying answers. That night, she pointed her instrument at Andromeda, our neighboring galaxy, a beautiful spiral floating 2.5 million light-years away. Vera spent months preparing to measure star speeds at different distances from the galactic center. This was routine, basic astronomy. Since Newton, we have known exactly how rotation works in space. The farther you are from the center, the slower you move. In our solar system, Mercury races around the Sun, while Neptune, way out at the edge, crawls along. This pattern has held true for 4 centuries. Vera expected Andromeda to follow the same established rules. The numbers appeared on her screen, and she frowned. Something was fundamentally and catastrophically wrong. Stars at the very edge of Andromeda were flying at speeds of 186 miles per second. Stars near the center were moving at the same impossible speed. According to every known law of physics, these stars should have been flung into space like passengers on a spinning ride, going way too fast. The galaxy should have torn itself apart long ago. Yet, Andromeda has existed for billions of years, perfectly stable and perfectly intact. Only 2 explanations existed. Either every physics law we have ever discovered is broken, or something massive is hiding inside these galaxies, something completely invisible, holding everything together with an immense gravitational force. Vera Rubin had just discovered that the universe is hiding something from us. But what she did not know then was just how much was missing. How do you weigh something as gigantic as a galaxy? Scientists figured out an elegant trick based on motion. To weigh Earth, you observe how fast the moon orbits us. The faster the moon travels, the stronger Earth's mass and gravity must be. Vera Rubin used this exact method with galaxies. She observed how stars orbit their galactic centers, and from their speed, she calculated the total mass needed to keep them in place. The math was confirmed, and the method was proven. Then came the shock. When Vera counted everything visible in Andromeda, every bright star, every gas cloud, every speck of cosmic dust, she found only 1/5 of the necessary mass. 80% was missing. Imagine a structural engineer calculating that your house should weigh 5 times more than it appears to keep standing. 80% of your house would be invisible. That is exactly what Vera discovered about galaxies. 80% unaccounted for. This was not a small error or an instrument malfunction. This was a fundamental problem with reality itself. Scientists call this the galaxy rotation problem, and it has been confirmed in thousands of galaxies across the universe. Every single one is missing most of its mass. This invisible mass is not randomly scattered far away. It is everywhere. It surrounds every galaxy and fills the space between the stars. Billions of invisible particles are passing through your body, your skin, your bones, and your brain right now. You do not feel anything. You cannot block them. They leave no trace whatsoever. Yet, this invisible substance represents 80% of everything that exists. You are living in a universe where most of reality is completely hidden from your senses. But what exactly is this invisible mass made of? Scientists needed a name for this elusive substance, and they called it dark matter. Not because it is black, but because it does not emit any light at all. It does not absorb light, nor does it reflect light. It is perfectly transparent to every form of electromagnetic radiation, a fact confirmed by decades of observation. Think of it like a ghost universe overlapping with ours. Dark matter exists in the same space we occupy. It just refuses to interact with anything we can detect. The only way it touches our world is through gravity. That is it. One single force connecting two separate realities. You cannot see dark matter or touch it. The only evidence of its presence is how it makes other objects move. Imagine a massive, invisible hand pushing the stars around in galaxies. You would never see the hand. You would only see the stars responding to its grip. Here is the disturbing part. The ratio is not random. The 85% invisible to 15% visible proportion is necessary for the universe to function. Change it even slightly, and everything falls apart. Galaxies would not form, stars would not ignite, and planets would not exist. We are like the tip of an iceberg, floating on an ocean we cannot perceive. Everything we see, every star, every planet, every human being, represents just 15% of reality. The other 85% exists in a realm completely beyond our senses. Some physicists compare this to living in a two-dimensional world. While a three-dimensional reality surrounds you, you would only notice strange, unexplainable effects. That is our situation with dark matter. If dark matter really exists, we should be able to detect it somehow. We should be able to track it down, study it, and understand what it is made of. That is when scientists launched the most extraordinary hunt in history. They decided to catch something that does not want to be caught, something that barely interacts with our world at all. The question became simple. How do you trap a ghost? Right now, this second, trillions of dark matter particles are passing through you, your chair, the floor beneath you, and the entire planet. They are moving at hundreds of miles per second. Nothing stops them, and nothing slows them down. One particle just went through your left eye, another through your heart, and thousands more through your lungs. As you breathe, you feel absolutely nothing. This has been happening every moment of your entire life, and every moment of human history. Scientists estimate that in one single second, about 100 billion dark matter particles pass through every square inch of your body. That is more particles flowing through you every second than there are stars in the Milky Way, a mind-boggling scale confirmed by calculations based on dark matter's estimated density in our galactic region. These particles do not care about matter the way we understand it. A wall of solid steel is as transparent to them as empty space. The entire Earth is transparent to them. They pass through the planet's core like it does not exist. Imagine being able to walk through walls, mountains, and planets. That is dark matter's reality. And it gets even stranger. Dark matter particles might be passing through each other too. Right inside your body, dark matter could be intersecting, overlapping, and moving in opposite directions through the same space. Think of two clouds of smoke. passing through each other without mixing. Some of these particles have been traveling through space for billions of years without ever hitting anything. They have crossed entire galaxies and passed through countless stars. They have witnessed the entire history of the universe, and they have never once touched anything solid. You are living inside an invisible ocean, an ocean so vast it contains 6 times more mass than all visible matter combined. You swim through it every day, you breathe it, and it flows through your DNA. Yet, you will never feel even a single particle. But scientists refuse to accept invisibility as an excuse. If these particles exist, they must interact with normal matter occasionally. Maybe once in a trillion collisions. Maybe once in a quadrillion. That is enough. That is what scientists decided to hunt for. That incredibly rare moment when dark matter finally touches something we can detect. Building that trap would require the most sensitive instruments humanity has ever created. But before we hunt dark matter, we need to understand what makes it so impossibly difficult to catch. Dark matter breaks every rule about how matter should behave. It is matter that refuses to act like matter. First, dark matter does not emit light. Every normal particle we know radiates some form of energy. Electrons emit photons, atoms emit heat, and even the coldest gas clouds in space emit faint radio waves. Dark matter is complete silence across the entire electromagnetic spectrum. Second, dark matter does not absorb light. When light passes through normal matter, some photons get absorbed. That is how we see things. Dark matter lets every single photon pass through unchanged. It is perfectly transparent to light of every wavelength, from radio waves to gamma rays. Third, dark matter does not reflect light. Shine the brightest laser in the universe at dark matter, and the beam passes straight through like shooting light through empty space. There is no surface to bounce off, no boundary to mark where dark matter begins or ends. Fourth, dark matter does not collide with normal matter, almost never. The odds of a dark matter particle hitting a normal atom are astronomically small. Scientists calculate that a dark matter particle could pass through a wall of lead-1, light-year thick, and probably not hit a single atom. That is 6 trillion miles of solid lead, still transparent to dark matter. Fifth, dark matter might not even collide with itself. Some theories suggest dark matter particles pass through each other as easily as they pass through us. This remains theoretical. Nobody knows for sure. So, what does dark matter actually do? It pulls. That is it. Dark matter exerts gravitational force. It attracts other matter through gravity. That is the only confirmed interaction we have detected. One force, one single connection to our reality. Imagine trying to study something that refuses to emit signals, refuses to absorb signals, refuses to reflect signals, and barely touches anything physical. You are essentially trying to study something that does not want to exist in the same universe as you. Yet, this impossible-to-detect substance holds galaxies together and structures the entire cosmos. Which raises an obvious question. If dark matter is this elusive, how can the weakest force in nature hold together the entire universe?
Doing all of that.
Here is the paradox that keeps physicists awake at night. Dark matter only interacts through gravity, and gravity is the weakest force in nature by far. A tiny fridge magnet can lift a paperclip against the gravitational pull of the entire Earth. One small magnet defeats the combined gravity of a planet, weighing 6 sextillion tons. That is how pathetically weak gravity is compared to electromagnetic force. Dark matter has no electromagnetic, strong nuclear, or weak nuclear force, just gravity. How then does it hold together objects containing trillions of stars? The answer lies in scale. Dark matter makes up for its weakness with overwhelming quantity. There is so much dark matter in a galaxy that its combined gravitational pull becomes enormous. Think of it like this. One ant cannot move a boulder, but a trillion ants working together can move a mountain. Every galaxy sits inside a massive halo of dark matter. These halos extend far beyond the visible edges of galaxies. Our Milky Way's dark matter halo reaches out roughly 600,000 light years, 3 times wider than the visible galaxy itself. This halo, confirmed by gravitational measurements, contains approximately 1 trillion times the mass of our Sun. That is 1 trillion solar masses of invisible matter surrounding us. All of it pulls on the visible stars and gas through gravity alone. The combined force is powerful enough to prevent the galaxy from flying apart despite its rotation speed. But here is what is truly strange. Dark matter does not clump together like normal matter. Normal matter collides, heats up, and condenses into dense objects like stars and planets. Dark matter cannot do this because it does not collide efficiently. Instead, it forms these enormous diffuse halos. Scientists think dark matter particles are constantly zooming through these halos at hundreds of miles per second. They orbit. They pass through each other, and they create a kind of invisible atmosphere around galaxies. Some researchers propose dark matter might occasionally interact through forces we have not discovered yet. Maybe a dark force that only affects dark matter. But what we know for certain is that gravity alone is sufficient to explain how dark matter structures the universe. The challenge now is proving dark matter exists beyond just gravitational evidence. That means detecting individual particles, and that means building a trap so sensitive it can catch something that almost never touches anything. Scientists decided to build exactly that. Imagine trying to hear a whisper during a thunderstorm. And now imagine that whisper is 1,000,000 times quieter. That is the challenge physicists face trying to detect dark matter. They need silence, perfect silence, and they need to listen very carefully. The most ambitious dark matter detector is called Lux Zeppelin. Scientists built it 1 mile underground in an abandoned gold mine in South Dakota. Why underground? Because cosmic rays from space constantly bombard Earth's surface, creating too much noise. Going underground blocks most cosmic radiation. The detector contains 7 tons of liquid xenon. Why xenon? Because it is extremely dense and pure. If a dark matter particle hits a xenon atom, it might create a tiny flash of light. That flash would be the first direct evidence that dark matter physically exists. But here is the problem. That flash would be incredibly faint. Scientists compare it to seeing a single candle burning on the moon observed from Earth. That is the level of sensitivity required. Any stray radiation would overwhelm the signal. So, they surrounded the xenon tank with 72,000 gallons of ultra-pure water to block outside radiation. They cooled the xenon to minus 100 degrees Celsius and eliminated every possible source of contamination, using materials with almost zero natural radioactivity. The detector can identify individual particle collisions. When something hits a xenon atom, it produces both light and electric charge, and measuring both helps distinguish dark matter from background radiation. The detector records millions of events every day, and computers analyze each one, filtering out cosmic rays, eliminating natural radioactivity, and removing seismic vibrations. What remains should be dark matter collisions. Should be. Scientists have run this experiment for years, analyzing billions of events and pushing the sensitivity limits further than anyone thought possible. Result: 0 dark matter particles detected. Not one. The detector has been running for years in perfect silence, waiting for a signal that never comes. It is like setting up the most sophisticated microphone in history and hearing nothing but emptiness. Other experiments have tried different approaches, using different materials, or looking for different types of interactions. All of them reported the same result. This creates a massive problem. Either dark matter particles are even more ghostly than we thought, or we are looking for the wrong thing entirely. Maybe the particle collisions we are waiting for simply do not happen. Scientists refuse to give up, but with each failed experiment, the mystery deepens. If we cannot detect dark matter directly, how can we prove it exists? That is when astronomers discovered something extraordinary, something that would provide the most dramatic evidence for dark matter anyone had ever seen. Let us talk about exactly how impossibly difficult dark matter detection actually is. Scientists need to detect a signal so weak, it defies comprehension. When a dark matter particle hits a xenon atom, it transfers a tiny amount of energy, about 1/100,000th, the energy of a single photon of visible light. That is the collision scientists are trying to measure. An impact that weak should not be detectable at all. To put this in perspective, the flash of light produced would be equivalent to detecting a single photon from a candle placed on the lunar surface, 239,000 miles away. You are trying to see signals that should not be visible to any instrument. The detectors use photomultiplier tubes that can detect individual photons. When a single photon hits the tube, it creates a cascade of electrons, amplifying the signal by millions of times. Even with this amplification, the dark matter signal barely rises above the background noise. Background noise comes from everywhere. Radioactive atoms in the surrounding rock, cosmic rays, and even the detector materials themselves. Every precaution has been taken. The xenon is purified to an incredible level. Even one radioactive atom per trillion would create too much noise. Scientists spent years developing purification techniques to reach this level, removing contaminants atom by atom. Despite all these precautions, thousands of background events occur every day. Each one must be carefully analyzed. Is it a cosmic ray, natural radioactivity, equipment noise, or the one event in a billion that might actually be dark matter? After years of operation, processing billions of collisions and filtering out every known source of background, the result remains the same. 0 confirmed dark matter detections. The candle on the moon remains invisible. This failure is reality telling us something profound. Dark matter is even stranger than our wildest theories predicted. Or perhaps we are chasing something that does not exist at all. But astronomers had one more trick up their sleeve. If they could not catch dark matter in a laboratory, maybe they could watch it in action across the cosmos. 20 years of searching, dozens of experiments, billions of dollars invested, and thousands of scientists dedicated their entire careers to finding dark matter particles. The results: complete silence. Lux Zeppelin in South Dakota, Xenon in Italy, Panda X in China. Every major dark matter experiment reports the same outcome: nothing detected. This is not just frustrating, it is scientifically terrifying. We built our entire model of the universe around dark matter. We calculated that it must exist, and our theories demand it. Yet, when we actually try to find it, the universe gives us nothing but emptiness. Every time scientists think they have found something, more careful analysis reveals mundane explanations: cosmic rays, equipment malfunction, statistical fluctuation. The ghost remains uncaught. This failure has pushed some physicists toward radical alternatives. Maybe dark matter does not exist. Maybe our understanding of gravity is wrong. But before we abandoned dark matter entirely, astronomers discovered something that provided the most spectacular confirmation anyone could ask for. They found dark matter separating from normal matter in real time. In 2006, astronomers detected something extraordinary. Two massive galaxy clusters were colliding in deep space. This was not a gentle merger. This was a violent, head-on collision happening at 2,900 miles per second, over 10 million miles per hour. Each cluster contained thousands of galaxies, trillions of stars, vast clouds of superheated gas, and, if dark matter exists, enormous halos of invisible matter surrounding everything. This collision would become the most important observation in dark matter research. Scientists call it the bullet cluster. Here is what made this collision so revealing. When two galaxy clusters collide, different materials behave differently. The individual galaxies pass through each other relatively easily because galaxies are mostly empty space. But the hot gas between the galaxies, which makes up most of the normal matter in the cluster, cannot pass through easily. When the gas clouds collide, they slam into each other, creating shock waves and heating up to hundreds of millions of degrees. The collision slows them down and leaves them behind in the center of the wreck. Astronomers can see this gas because it glows in X-rays, showing it concentrated exactly where the impact happened. The gas marks the point of impact. Now, here is where it gets interesting. Astronomers can measure where the mass is located using gravitational lensing. Massive objects bend space-time, which deflects light from distant galaxies behind them. By measuring these distortions, scientists can map where mass exists, whether visible or invisible. They measured the bullet cluster's gravitational field and found something shocking. The majority of the mass is not where the gas is. The mass is surrounding the galaxies themselves. The mass passed right through the collision, almost unaffected. Think about what this means. The visible matter, the glowing gas, stayed behind in the collision. It interacted with itself and got stuck. But most of the gravitational mass kept moving. It passed through the collision like the gas did not exist. This is exactly what dark matter should do. Dark matter does not interact with normal matter. It does not collide with gas. It just floats through everything, guided only by gravity. The dark matter halos from both clusters passed through each other and continued onward with the galaxies. Scientists can literally see the separation. The gas sits in the middle, and the gravitational mass sits on either side. They photographed the moment when dark matter and normal matter separated. This is direct visual evidence that invisible matter exists independently from visible matter. This observation is considered the strongest proof of dark matter's existence. It is hard to explain with modified gravity theories because the mass and the matter are in different places. You are not just seeing gravitational anomalies. You are watching matter behave as if there are two types, one that interacts and one that does not. Some scientists call this the smoking gun of dark matter research. The bullet cluster proved that dark matter exists. Now scientists need to figure out what it actually is. If dark matter exists, it must be made of particles, but what kind? Scientists have proposed candidates ranging from the absurdly heavy to the impossibly light. The most popular theory involves WIMPs, which stands for Weakly Interacting Massive Particles. Despite the silly name, WIMPs are serious candidates. These hypothetical particles would be 50 to 1,000 times heavier than a proton, making them heavier than any normal atom. WIMPs would have been created in the Big Bang. In the first moments of the universe, temperatures were so extreme that these stable exotic particles could form and survive for the entire age of the universe. Scientists love WIMPs because they emerge naturally from several extensions to the standard model of particle physics. But there is a problem. We have not found them. Despite 20 years of searching with increasingly sensitive detectors, no confirmed WIMP collisions have been detected. Either WIMPs interact even more weakly than predicted, or they do not exist at all. Some physicists propose even heavier candidates or suggest that dark matter might instead be countless tiny black holes formed in the Big Bang, primordial black holes. Recent observations, however, have ruled out most mass ranges for these black holes. They cannot account for all dark matter, though they might contribute a small percentage. The heavier candidates have mostly been eliminated or pushed to the margins of possibility. That leaves scientists looking at the opposite extreme. What if dark matter particles are not heavy at all? What if they are almost impossibly light? Here is an idea that sounds like fiction, but is taken seriously by physicists. What if dark matter forms its own complete universe alongside ours? Think about our visible universe. We have atoms, molecules, chemistry, and electromagnetic forces that let everything stick together. Now imagine dark matter has similar complexity. What if dark matter particles can combine into dark atoms? What if dark atoms form dark molecules? What if there are dark chemical reactions we cannot observe? Physicists call this the hidden sector theory. In this scenario, dark matter experiences its own forces, a dark electromagnetism, a dark strong force, and a dark weak force. These forces only affect dark matter particles. They are completely invisible to our instruments because our instruments are made of normal matter. Under hidden sector theories, dark matter could form dark planets, dark stars, or maybe even dark galaxies within our galaxies. These structures would exist in the same physical space as Earth. You could be standing inside a dark matter mountain right now. You would walk through it like it was not there because, to normal matter, it is not there. Could dark matter support complexity? Could there be dark matter life? This sounds absurd, but if dark matter is 85% of all matter, why would it be simpler than our 15%? Maybe we are the simple universe. Dark matter could have its own history completely separate from ours. Right now, Earth could be passing through dark matter structures as we orbit our sun. Dark matter currents could flow past us. We detect nothing beyond subtle gravitational effects. The hidden sector theory makes testable predictions. If dark matter has its own forces, those forces might leak into our sector in specific ways. Certain particle collisions at CERN might produce dark sector particles. These would appear as missing energy, but with unique patterns. The most bizarre extension of this idea is the proposal that dark matter exists in a parallel dimension. Not a science fiction dimension, but a real physical dimension we cannot access. String theory predicts this, suggesting up to 7 extra dimensions beyond our 3. Dark matter might exist partly or entirely in these extra dimensions. From our perspective, dark matter appears as particles in our 3 dimensions, but most of its existence extends into dimensions we cannot see. We only interact with the tiny fraction that overlaps with our dimensions. This could explain why gravity is the only interaction we detect. Electromagnetic, strong, and weak forces might be locked to our 3 dimensions, but gravity could propagate through all dimensions. This theory predicts that if extra dimensions exist, gravity itself might leak into them, making gravity appear weaker in our 3 dimensions than it should be. This is serious physics, trying to explain why 85% of the universe hides from us. Maybe it is not hiding. Maybe we are just looking in the wrong dimensions. But regardless of where dark matter exists or what it is made of, one fact remains undeniable. Without dark matter, nothing would exist at all. In the first fraction of a second after the Big Bang, dark matter was created alongside normal matter. In those earliest moments, the universe was incredibly uniform, almost perfectly smooth. This creates a massive problem. If the universe was that smooth, how did it develop structure? You cannot build galaxies from uniformity. Here is where dark matter becomes essential. Normal matter in the early universe was trapped. It was locked in a hot plasma of electrons and photons. Any density variation in normal matter got erased because light pressure kept pushing the particles apart. They could not clump together. Dark matter faced no such problem. Dark matter does not interact with light and does not feel radiation pressure. So, while normal matter remained stuck in a boiling plasma, dark matter was already beginning its work. Wherever dark matter happened to be slightly more concentrated, gravity pulled more dark matter toward it. These concentrations grew, forming structures invisibly. All of this happened with no light to mark the events. Dark matter got a massive head start. Think of it like a snowball rolling down a hill. It starts tiny, but it gathers more snow as it rolls, growing bigger and bigger through gravitational accumulation without resistance. 380,000 years after the Big Bang, the universe finally cooled enough for normal matter to break free from the plasma. When normal matter became free, it found a universe already structured by dark matter. Invisible scaffolding filled space. Dark matter halos marked the locations where the first galaxies would form. Normal matter fell into these gravitational wells like water-finding valleys. Dark matter prepared the mold, and normal matter filled the mold. Without the mold, normal matter would have dispersed evenly through space, forming no structures, just a thin, uniform gas, expanding forever into emptiness. Every step of cosmic evolution, from the first stars that created heavy elements to the formation of rocky planets, required dark matter's gravitational framework. The calcium in your bones, the iron in your blood, and the oxygen you breathe all came from stars that owed their existence to invisible matter. Our entire Milky Way galaxy sits inside a dark matter halo that extends 600,000 light-years across, containing 1 trillion solar masses of dark matter. Its gravity holds our galaxy together. We are not living in a galaxy with some dark matter around it. We are living inside a dark matter structure that happens to have some visible matter sprinkled in the center. You exist because dark matter got a head start of 380,000 years. That head start built the framework for everything. WIMPs have dominated dark matter research for decades, but after years of null results, physicists are exploring alternative candidates. Two particularly interesting possibilities are axions and sterile neutrinos. Both would be radically different from WIMPs. Axions would be incredibly light, about 1 trillion times lighter than an electron, almost massless. But there would be an enormous number of them. Scientists calculate that approximately 10 billion axions would occupy every inch of space in our galaxy. Axions would behave more like waves than particles, forming a kind of quantum field permeating the galaxy. This field would oscillate, or vibrate, at a specific frequency determined by the axion's mass. The entire dark matter halo would be humming with this oscillation. Scientists built an experiment called ADMX, the Axion Dark Matter Experiment, a highly tuned radio receiver. If axions exist, their oscillations might convert to electromagnetic waves inside a strong magnetic field. ADMX is trying to detect those waves, but the challenge is finding the right frequency, as the exact mass of the axion is unknown. Now, let us consider sterile neutrinos. Regular neutrinos are known to be barely interacting, but they are too light and too fast to be dark matter. Scientists propose that heavier versions might exist, called sterile neutrinos. They would be thousands of times heavier than regular neutrinos, but still much lighter than protons. Sterile neutrinos would be even more ghostly than regular neutrinos, interacting only through gravity. However, they might very rarely decay. When they decay, they would produce regular particles we can detect, such as an X-ray photon with a very specific energy. In 2014, multiple research teams reported detecting an unusual X-ray line that matched predictions for sterile neutrino decay, but the signal was weak, and the debate continues. The failure to catch dark matter has led some physicists to a radical alternative: modified gravity. Instead of inventing invisible particles, some propose changing how gravity works. The idea is simple. At very large distances or very low accelerations, gravity might behave differently than Newton or Einstein predicted. In this scenario, there is no dark matter at all. The galaxy rotation curves that convinced us dark matter exists are actually showing us that our gravity equations are incomplete. This would mean Einstein's general relativity needs correction, overturning a century of confirmed predictions. The most famous version is called MOND, or Modified Newtonian Dynamics. MOND proposes that when accelerations become extremely tiny, like at the edges of galaxies, gravity gets stronger than predicted. This extra pull explains the star's unexpectedly high speeds without the need for dark matter. MOND has one universal parameter, one number that sets where the modification kicks in. This single parameter works for all galaxies, which is highly impressive. Dark matter models, by contrast, need to fine-tune invisible halos for each galaxy. But MOND has serious problems. First, it is not a complete theory. It is an empirical rule without a theoretical foundation, lacking the depth of Einstein's relativity. Second, MOND struggles with massive galaxy clusters. You still need some invisible matter to explain the total mass. Third, MOND fundamentally cannot explain the bullet cluster. Remember that collision? The gravitational mass separated from the visible matter. With MOND, gravity is produced by visible matter, so the gravitational center should be where the visible matter is. The observation clearly shows mass where there is no visible matter. The scientific community has largely moved away from pure modified gravity, but MOND's successes still puzzle everyone. What if our entire framework for understanding reality needs to be rebuilt? What if we are wrong about both dark matter and gravity? This has happened before in science. Newton's gravity worked perfectly for centuries until Einstein showed it was an approximation. Maybe Einstein's general relativity is also an approximation. Maybe our understanding of matter is incomplete. Dark matter might be our generation's luminiferous ether, the invisible substance that scientists in the 1800s believed light traveled through, which Einstein later proved did not exist. We are building cosmology on dark matter, constructing models of the universe's history that assume it exists. If we are wrong, decades of work collapses. But this is also exciting. Science advances through revolutions. Maybe we are due for another one. The signs are there. We cannot detect dark matter, and modified gravity does not work. When two opposite solutions both fail, perhaps the problem itself is wrong. We are at a critical moment in scientific history. The next decade will be crucial, with new telescopes and experiments coming online. The first major step is the European Space Agency's Euclid telescope, launched in July 2023. Euclid will spend 6 years creating the most detailed map of dark matter ever attempted. Euclid is designed specifically to map the invisible universe. It will photograph 1/3 of the entire sky, billions of galaxies. And for each, it will measure precise shapes and distances. This technique uses weak gravitational lensing, where dark matter's gravity creates tiny, barely noticeable stretching or warping of distant galaxies. By analyzing millions of galaxies, Euclid can statistically reconstruct where dark matter is located throughout cosmic history. The data will reveal the cosmic web in unprecedented detail, the filaments and voids of the universe's large-scale structure, with dark matter forming the skeleton. Euclid will not just map static structure, it will measure cosmic history by tracing how dark matter evolved over time. A crucial test for different dark matter particle candidates. It will constrain whether dark matter is made of WIMPs or axions. Complementing Euclid is the Nancy Grace Roman Space Telescope, set to launch around 2027. Roman will look deeper into specific regions with greater capabilities. Its mirror is nearly twice the width of Euclid's, allowing it to see fainter, more distant galaxies further back in time. Roman's key mission is to study both dark matter and dark energy, the mysterious force causing the universe's expansion to accelerate. Dark energy makes up about 68% of the universe, and dark matter is 27%, leaving normal matter at just 5%. The balance between dark matter, which creates structure through gravity, and dark energy, which pushes structure apart through cosmic expansion, determines the fate of the universe. Roman will measure this balance precisely by observing distant, exploding stars that serve as cosmic measuring sticks. The combination of Euclid and Roman will provide unprecedented data about the invisible universe. By the early 2030s, we will have detailed maps showing dark matter throughout cosmic history. We will see which theoretical predictions match observations and which fail. This might finally solve the mystery, or it might deepen it if the data contradicts all existing theories. 85% of the universe is invisible to us. Everything we have ever observed represents just 15% of reality. Some find this depressing, but this ignorance is our greatest opportunity. It means the biggest discoveries in human history are still ahead of us. 50 years ago, Vera Rubin noticed something strange that opened up an entirely new field of research. Since then, thousands of scientists have worked to solve this mystery, building detectors underground and launching telescopes into space. We have not found the answer yet, but every negative result eliminates possibilities. The search continues. New experiments are starting, exploring theories that sound like science fiction. Extra dimensions, hidden sectors, and exotic quantum fields. When we finally understand what dark matter actually is, it will change everything. The discovery could be this century's equivalent of quantum mechanics or relativity. We are living through this right now, this moment in history, when humanity is grappling with the realization that most of reality is hidden from us. The darkness is not empty. It is full of answers waiting to be discovered. If this exploration into the invisible reality changed how you see the cosmos, watch this next on The Truth About the Black Hole Information Paradox to keep the story going and understand where the information from a previous universe might hide.